Hello, this is Nathanael again. Last time we have been discussing about distribution design. Specifically, we have been talking about fragmentation and allocation and the combination of this fragmentation and allocation. Today, I will be talking about distributed query processing. So here we assume the database is fragmented and distributed over the network sites. And now we deal with processing queries over these distributed network sites. Specifically, I will be talking about query decomposition and localization, join ordering, distributed query optimization, and adaptive query processing as part of the distributed query processing topic. When we say query processing in distributed database management system, it's all about transforming high-level user queries to low-level data manipulation commands. When we say high-level user queries, these are declarative queries or structured query language, or we can also say these are relational calculus, which are user-level queries. And this will be fed to the query processor component, and the result of this query processor component is called relational algebra, or in other words, low-level data manipulation commands that can be localized, decomposed and localized per network site level. The components of query processing are query language, query execution, and query optimization. So while talking about query processing, we have to deal with query language, query execution, steps, and the query optimization techniques. So when we say query language, it's a relational calculus or a general language. It's user-level language. We call it intergalactic data speak or structured query language. This is all about dealing with declarative language called structured query language. When we say query execution, these are steps that one goes through in executing high-level declarative user queries like relational calculus or structured query language. When we say query optimization, it's all about determining the best execution plan in a distributed environment. By the way, query optimization could be also applied in a centralized environment. So when we say optimization of queries, we are referring to the process that we go through to find the best execution plan for our applications or queries. For the pedagogical ease, we use homogeneous distributed database management system, or we assume homogeneity over distributed database management systems. That means we mainly consider similar type of or homogeneous type of database management systems distributed over the network sites, and the structure and the model of the database that we are going to consider is the same. In order to understand the benefits of query processing and the need for optimizing queries in both centralized and distributed database management system environment, let's take this one example. Here we do have a query that projects employee name from the natural join of relation employee and assignment by using a criteria responsibility is equal to manager. So here, employee relation has information regarding the employee, like employee name, employee number. And on the other hand, assignment has employee number as a foreign key and other informations like responsibility that describes what responsibility is the employee assigned to. So in order to execute or process this query, in order to transform this query, this relational calculus to relational algebra, we could use multiple strategies. Among them, two of the possible strategies are listed here. The first strategy computes Cartesian product between the two relations and apply join and selection operations over this intermediate result of the Cartesian product, and ultimately projection of employee name is performed. When you come to strategy two first performs selection or horizontal fragmentation on relation assignment. Then the intermediate result from this operation is further equi-joined with relation employee, and ultimately the employee name attribute is projected. So from what we know from session 2 or chapter 2 of or part 2 of our lecture, Cartesian products are more expensive than other types of joins like equi-join or inner join. So for that purpose, we can generally suggest the execution of the strategy to rather than strategy one, because strategy one is going to need much space and computational time. But in relation to strategy one, strategy two requires or demands or takes smaller computational time and resource. So we might suggest, strategy two is better than strategy one, depending on the complexity of operations that we are applying. But let's expand or extend this concept of query optimization in a distributed database management system environment. Let's take this assumption. Assume we have uh, both relations, assignment and employee, fragmented and distributed over the network. And again, assume we are at site 5 where there is no local data regarding employee and assignment. Let's say site 1 holds all assignments whose employee number is less than or equal to E3. Site 2 holds all assignments whose employee number is greater than E3. And site 3 and site 4 holds data for employee table. For site 3 holds employees whose employee number less than or equal to E3, and site 4 holds employees whose employee number greater than E3. So as you can see here, the horizontal fragmentation criteria that we used for site 1 and site 3 is the same, and the horizontal fragmentation criteria we use for site 2 and site 4 is the same. So here we are supposed to issue query to all of these 4 sites pertinent to the query that we selected here, the strategy 2. So we can decompose and execute our query in various ways, among which these 2 are the main ones. In case of the first execution procedure, the first execution considers the fragmentation and distribution of data. So it first performs selection on assignment 1, which is located in site 1, and selection on assignment 2, which is located in site 2. Then the primary horizontal fragment it gets from these 2 sites is further transferred to site 3 and site 4. As we have already discussed, site 3 holds data on employee 1, which is all employees with employee number less than or equal to E3. And site 4 holds employee data whose employee number is greater than E3. So at site 3, after transferring assignment 1 and assignment 2 to site 1, site 3, and site 4, we can further perform join operation. So in site 3, we can perform equi-join between employee 1 and assignment 1 prime, which is the primary horizontal fragment of assignment 1. And in site 4, we can perform equi-join between employee 2 and the primary horizontal fragment of assignment 2, which is transferred from site 2. Then further, we can transfer employee 1 prime and employee 2 prime, which are the result of the join operation between employee and assignment sub-relations. And we can union the result to get, you can union the sub-relations from site 3 and site 4 to get the desired result. In case of the second strategy, the second decomposition and execution strategy, the second one does not really consider the distribution and fragmentation of the relation. It simply collects or transfers all of the fragments to a single site, site 5. For instance, in the first case, it transfers employee 1 from site 3 and employee 2 from site 4. And again, the same is true for assignment 1 and assignment 2. It transfers assignment 1 and assignment 2 from site 1 and site 2 in their entirety. Then after collecting and unioning both of these relations into one, then it performs selection on assignment relation, which is constructed from the union of assignment 1 and assignment 2, and further equi-joins the result of this one with the union of employee 1 and employee 2. So as you can see from these 2 relations, it's intuitively evident that the 2 strategies of executing the same query might not yield the same computational complexity. So let's compute the computational complexity or the resource demands of each of these queries so that we understand the procedures we follow while executing or decomposing queries in a distributed environment affects the resource requirements of queries. In order to calculate the cost of executing query in using strategy 1 and strategy 2, we have to first set some benchmarks so that our simple cost calculation model utilizes them. So the first benchmark is the size of employee and assignment. The size of employee is 400 tuples and the size of assignment is 1000 tuples. The tuple access cost, the cost that we spend to access a single tuple in a relation, is said to be 1 unit. And the cost that we require to transfer one tuple from a site to another site is estimated to be 10 units. So according to strategy 1 is a query execution strategy that considers distribution of fragments over the network, and it tries to apply selection and projection before transferring data. This is usually recommended because the tuple transfer cost is larger than tuple access cost. So it's usually recommended to access and filter fragments in a way reducing their size before transferring them to the target site. So accordingly, the strategy 1 first produces assignment prime, which is the union of assignment 1 prime and assignment 2 prime, which belongs to site 1 and site 2. So assignment 1 prime is a sub-relation that we get by applying a primary horizontal fragmentation on assignment 1. And further, assignment 1 is currently located in site 1, as you can see in this diagram, according to strategy 1. And assignment 2 prime is again a primary horizontal fragmentation of assignment 2 relation, which is currently placed in site 2. So the first operation strategy 1 executes is producing assignment 1 prime and assignment 2 prime. So in order to produce assignment 1 prime and assignment 2 prime from assignment 1 and assignment 2 respectively, the query has to access 10 tuples from each site. And in order to calculate the cost of producing assignment 1 prime, for instance, you have to multiply the number of tuples in the relation, in the sub-relation, by the tuple access cost. And in order to get the production cost of both of these sub-relations, you can simply multiply the result of product of the number of tuples with tuple access cost by 2. So accordingly, here to produce assignment prime, which is a summation of assignment 1 prime and assignment 2 prime, then we simply add the number of tuples that our query access from site 1 with the number of tuples that our query access from site 2, and we multiply both of these with tuple access cost. Accordingly, the cost of producing assignment prime is 20. According to strategy 1, after getting assignment 1 prime and assignment 2 prime, that means after getting assignment prime, which is a union of these two, the second operation is transfer of these sub-relations or primary horizontal fragments. So for the first site, the transfer is done from site 1 to site 3, and for the second part, the transfer of primary horizontal fragment is done from site 2 to site 4. So here to transfer assignment 1 prime from site 1 to site 3 can be calculated as the number of tuples in assignment 1 prime times the tuple transfer cost, and the same is true for transferring assignment 2 prime from site 2 to site 4. So in order to get the total cost of transferring assignment prime, which is the sum of assignment 1 prime and assignment 2 prime, we can simply add the number of tuples in each site, which is 10, and multiply it with the tuple transfer cost, which is again 10 units. So the transfer cost for assignment prime from each of site 1 and site 2 to site 3 and site 4 respectively is 20 times tuple transfer cost, which is 20 times 10. And finally, the result is 200. And according to the same strategy, the third step would be to perform equi-join uh, with what we have from site 1 and what we already have in site 3 for the left side, and what we have from site 2 and what we already got in site 4. So in this case, for instance, the next step of execution um, performs the equi-join between employee 1 and assignment 1 prime at site 3, and in site 4 it performs the equi-join between employee 2 and assignment 2 prime by using employee number as a join attribute. And finally, this operation produces employee 1 prime and employee 2 prime. So the union of these two subrelations yields employee prime. So in order to produce employee prime, the total cost would be the number of tuples that this join operation access in each of those relations. So for instance, in the first case, in site 3, since employee 1 and assignment 1 prime are constructed from uh, the same fragmentation condition or horizontal fragmentation condition, then the number of access, the maximum number of accesses to tuples in each of these relations is said to be the minimum number of tuples in any of these two subrelations. And the same is true for this one. So during our assumption, we said the total number of managers in the assumption in the assignment table or relation is 20, and data is distributed uniformly across the network sites. So for that purpose, we assume assignment 1 prime is exactly 10 tuples large, and assignment 2 prime is also 10 tuple size, 10 tuples large. So because of this, the join operation between employee 2 and assignment 2 prime, and also the join operation between employee 1 and assignment 1 prime yields exactly or accesses exactly 10 tuples from each of these subrelations. So accordingly, for the first site, for instance, to produce employee 1 prime, the operator simply accesses 10 tuples from employee 1 and 10 tuples from assignment 1 prime, and it multiplies this with the tuple access cost, which is 1. And in order to show the similarity between the cost of joining these two relations, then you can simply multiply the result by 2. You can simply calculate the cost of producing employee 1 prime and add the result to the cost of producing employee 2 prime. So which gives the cost of producing employee prime, which is the union of employee 1 and employee 2 prime. So accordingly, the cost of producing employee prime, imp prime, is 10 plus 10 times tuple access cost times 2, which is 40 units. And after this, the strategy 1 transfers the intermediate result employee 1 prime and employee 2 prime to the point of use, which is site 5. So the tuple transfer cost is 10, but the current size of imp 1 prime and imp 2 prime is 10 for each. So the tuple size of both of these subrelations employee 1 prime and employee 2 prime is 20. So in order to calculate the transfer of employee prime to result site, which is site 5, we can simply multiply 20 by the tuple transfer cost. 20 by 10 is again 200, because tuple transfer cost is 10. So ultimately we get the total cost of 460 for strategy 1. So if we execute the previous query by using strategy 1, the total cost would be 460 units. We didn't say any specific things about the nature of the unit. This is simply for the ease of pedagogy. When you come to strategy 2, as you can see from this diagram to the right, this strategy does not consider any distribution. It does not try to benefit from applying selections before transferring tuples or fragments, because usually in query optimization tasks, it's recommended to apply selection per site level and transfers them after reducing their size by applying different projection selection. Hence, here the strategy 2 tries to merge all related fragments into one and transfers them to the target site, and it performs all join and primary horizontal fragmentations in the site where the data is required. So from this, we can gracefully suspect that this strategy is going to give us a poor performance. But let's see this experimentally. So the first operation here is to merge employee 1 and employee 2 fragments from site 3 and 4 and transfer them to the point of use, which is site 5. So in order to transfer employee to site 5, you have to spend a cost equivalent to number of tuples of employee relation times tuple transfer cost. So as it is given in our benchmark, the number of tuples of employee table is 400 and the tuple transfer cost is 10. So the cost of transferring employee relation from site 3 and site 4 to site 5 is 4,000 units. The second operation, according to strategy 1, is transferring assignment relation. Further, assignment should be constituted from assignment 1 and assignment 2, which are in turn located at site 1 and site 2. So in order to transfer assignment 1 and assignment 2 from site 1 and site 2 to site 5, the cost would be the number of tuples of both of these relations times tuple transfer cost. So the number of tuples of assignment as it is given here is 1,000. So 1,000 times tuple transfer cost is 10,000. The third operation here is producing assignment prime by applying primary horizontal fragmentation on assignment relation. So here producing assignment prime requires access to at least n number of tuples, where n is the size of the fragment. So for that purpose, the cost of producing assignment prime is calculated as the number of tuples of that relation times tuple access cost. So the number of tuples of that relation is 1,000 and tuple access cost is 1. So the cost of producing assignment prime, which is a primary horizontal fragment applied on the primary horizontal fragment after applying a selection criteria responsibility is equal to manager on assignment relation, then it's calculated to be 1,000. Then finally, the intermediate result, which is the result of applying primary horizontal fragmentation on assignment relation and the merged employee relation. So there is after merging these two relations separately and after applying primary horizontal fragmentation on assignment 1, an equijoin is performed according to strategy 2. So the equijoin performed on two relations which does not share the same fragmentation criteria is the multiple of their tuples. So in the first case, producing assignment prime yields 20 tuples because we said assignment prime to the maximum holds 20 managers or 20 tuples that belongs to managers. So for that purpose, the number of cardinality of assignment prime is 20, but employee prime has a size of 400 tuples. So the equijoin between employee and assignment prime is 400 times 20. Then the tuple access cost of each tuple is 1. So in order to calculate the cost of applying equijoin between employee and assignment prime, we have to multiply the number of tuples of each relation with the tuple access cost. So 400 tuples times 20 tuples times tuple access cost, which is 1, yields 8,000. So generally, the amount of units or the costs that we need to execute query 1 according to strategy 2 is 23,000. what does this computation tell us? What is the semantics behind this computation? You might have a very optimal query for centralized database system, but this optimal query for centralized database system might not perform well in distributed database system. So it's always important to carefully select procedural strategies that you use while working on or optimizing your queries in distributed database environment. So a query that has the best strategy might yield better performance in the distributed database environment, and a good query in centralized environment that doesn't have a good strategy for distributed database environment might yield poor performance. Now let's talk about the objectives of query optimization. So the main objective of query optimization is to minimize a cost function, where cost function is comprised of input-output cost, CPU cost, and communication cost. So here we are assuming a very simpler type of cost model in which there is only input-output cost, CPU cost, and communication cost as an argument. But the weight of each of these operands might differ from environment to environment. For instance, in wide area networks, communication cost may dominate, and it might vary by much. When we say communication cost, it means cost of bandwidth, speed, and protocol overhead. In case of local area networks, for instance, the communication cost might not be that dominant, but the total cost function might be considered. You know, when we say total cost function, the input-output cost, CPU cost, might dominate over the communication cost. But this query optimization can also maximize throughput. Okay, in addition to minimizing a cost function, the query optimization could also maximize the throughput or the amount of time that you require to process or to accomplish some task. Since we are expressing the outcome of our query optimizer in terms of relational algebra, it's important to know the complexity of various relational operators. We assume relations of cardinality n while discussing about the complexity of relational algebra operators, and we also assume sequential scans rather than random scans. So for operations like select and project without any duplicate elimination, the big O complexity of these operations is O of n, where n is the cardinality of relations. If you do not know about the big O omega of any algorithms, I recommend you to read about the time and space complexity of algorithms. So for the other operations like project and group by, for project with duplicate elimination and group by, the big O or the complexity, the time complexity of these operations in the worst case scenario is calculated as O of n times log n, which is a bit larger than O of n. For join, semi-join, division, and other set operators, the time complexity of these operators, assuming the cardinality of n of relation and sequential scan, is O of big O of n times log n. In our previous slide, we have been discussing about the expensiveness of Cartesian product. So the time complexity of Cartesian product is O of n squared, so it's more to quadratic. There are two types of query optimizers. The first one is based on exhaustive search, and the second one is heuristic. The exhaustive search based techniques are cost-based techniques, and they are optimal, but their complexity is combinatorial. That means they are mainly mainly intended to get the optimal result by exhaustively traversing through a set of solution spaces. But when we come to heuristic approach, these heuristic approaches are not optimal. They are mainly based on a function called heuristic function that tells them how far they are from the desired solution space. For instance, tasks like regrouping common sub-expressions, performing selection and projection first before transfer of fragments, replacing a join by a join by a series of semi-joins. Reorder of operations to reduce intermediate relation size. Optimizing individual operations can be considered as query optimizers that employ heuristic approach. When you come to optimization granularity, it can be further divided into single query at a time granularity and multiple queries at a time, or interquery granularity. When we see single query at a time, you cannot use common intermediate results. That means only one query is executed at a time. So there is no chance for you to execute, or for the database management system to execute more than one queries at a time. And because of this, the only intermediate relations that you can get is from the query that's being executed at a time. So for that purpose, this query cannot use common intermediate results. These common intermediate results in multi-table query scenario improve the performance of access of relations, because you could access intermediate results of other queries by saving computational resources that might be required to access same results. In case of multiple queries at a time granularity, it's efficient if many similar queries are available. But the setback for this type of optimization granularity is that the decision space is much larger, because multiple queries are supposed to run concurrently. So in this case, queries can share their intermediate results, so that improving the overall performance of the query processing. We can also divide optimization by its timing. Query optimization can be performed at compile time. We call it static optimization. We can also perform query optimization at runtime. It's called dynamic optimization. And we can also compile using a static algorithms. And whenever the error rate, or whenever the amount of errors that we get is greater than the threshold, then we can apply dynamic optimization techniques to re-optimize your previous configuration. So this is called hybrid optimization technique that applies both static and dynamic. It starts by static optimization, or it starts by optimizing your query at compile time. Then whenever it faces a large difference between the expected and the expected and the actual outcome in terms of estimated size of fragments, then dynamic optimization is triggered. For query optimization, we also need database statistics. For instance, when we optimize queries, we have to deal with the size of fragments that has to be transferred from one side to another side. So for that purpose, you need database statistics like relation level statistics, like cardinality, size of tuple, fraction of tuples participating in any operation, like in a join operation with another relation. Attribute level database statistics like cardinality of domain, actual number of distinct values is required. We can also further discuss query optimization based on the varieties in decision sites. Query could be optimized centrally, so we call it centralized query optimization. In this type of query optimization, a single site determines the best schedule. It's among the simplest type of query optimization techniques, where a single site is responsible to plan the best schedule. But in this case, the single scheduler, or the single entity that determines the best schedule, need to have complete information on the global conceptual schema, or the entire distributed database. The other type of query optimization is called distributed query optimization, where most nodes or network sites or database management systems are responsible to contribute or cooperate to come up with the best global schedule. In this kind of operation, each node in a distributed database environment is required to know only its local information, but there is a cost of cooperation between different nodes or network sites in the distributed database environment. The other query optimization classification from the perspective of decision sites is hybrid. In this kind of approach, one site determines the global schedule and each site optimizes the local subqueries according to the global schedule. That being said about the importance of processing and optimizing queries in both centralized and distributed database environment, let's talk in detail about query processing. And now we will start by discussing the layers of distributed query processing. So distributed query processing as a sequence of process starts with query decomposition. The query decomposition component accepts calculus query on global relations, and these calculus queries are usually referred to as declarative queries, and produces algebraic queries on global relations by using the global schema of that distributed database system. The second component in this sequence of process is data localization. The data localization component of distributed query processing accepts algebraic query on global relations. That means data localization accepts queries that does not know about the distribution details of the distributed database system. And by using the fragment schema, it will transform this algebraic query on global relations to algebraic queries on local relations or fragment queries. Distributed optimization, the third component in distributed query processing, accepts fragment queries, which are aware of the distribution details of your distributed database system. And by using the allocation schema or information about details of the allocation, it will transform this fragment query into distributed query execution plan. And finally, the distributed query execution plan is executed by using distributed execution component in the local site. Look, the first three components of distributed query processing are executed at control site or at the coordinator site. They use global schema, fragment schema, and allocation schema respectively. But distributed query execution plan is supposed to be executed at local sites where the fragment is located. Now let's talk about each of these components in the distributed query processing path in detail. The first component in distributed query processing is query decomposition. Query decomposition operations are almost more or less the same in both centralized and distributed database environment. So they take input as calculus query on global relations and execute operations like normalization, analysis, simplification, and restructuring. When we say normalization, the main purpose of normalization is to reduce redundant data and to reorganize the data so that the query is executed on this fragment or relation performs well. So in terms of calculus query or in terms of query decomposition, the principles behind query decomposition, normalization is simply transforming the calculus query into conjunctive normal form or disjunctive normal form. So it's there to manipulate query quantifiers and qualification. When you come to analysis is there only to detect and reject incorrect queries. Queries could be incorrect, one, if they are contradictory with each other, or if they have semantic incorrectness. The third operation that you could apply while decomposing calculus query into relational query is that simplification. During simplification, redundant predicates will be eliminated. In the analysis phase, you will come up with a set of simple predicates or mini-term predicates which are correct and which eliminates redundancy in general from the data perspective. But in the simplification phase, you accept this set of predicates and try to eliminate those which are redundant. After eliminating redundant simple predicates and the mini-term predicates, the last operation in query decomposition is restructuring the calculus query in algebraic query form by using different transformation rules. Some of the rules, for instance, would be in declarative language statement side, for instance, we do have a where clause that helps to select some sort of tuples from target relation. So this where clause could be transformed by using a rule which transforms where clause to selection operation of relational algebra. Again, a column listing clause, which is select, in calculus query or declarative language statement structured query language SQL can be further transformed into projection operation of relational algebra. So you can simply transform these calculus queries into equivalent algebraic queries by using various transformation rules. You can find these details of these rules in your textbook, which is Principles of Distributed Database Systems. Let's see some of the operations of query decomposition by example. Let's take one application, which is an application that finds the names of employees who have been working on project P1 for 12 or 24 months. So the declarative language equivalent of this application is written as select employee name from employee and assignment. These two are relations where employee.employee number is equal to assignment.employee number, and assignment.project number is equal to P1, and duration is equal to 12 or duration is equal to 24. So given this declarative statement or declarative query or calculus query, normalization, the first step in query decomposition, transforms this declarative query into either conjunctive normal form or disjunctive normal form. So to transform this query into conjunctive normal form, we take the different attributes that are subject for comparison in our simple predicates or mini-term predicates. So we have, for instance, one attribute, employee.employee number. So employee number of employee relation is one attribute here, and employee number of assignment is also another attribute. We do have project number of assignment and duration as candidates for this selection operation. So in order to transform this declarative query into conjunctive normal form, we can simply convert AND operations to conjunction and OR operations to disjunction. So the conjunctive normal form equivalent of this query is written as employee.employee number is equal to assignment.employee number, and assignment.project number is equal to P1, and duration is equal to 12 or duration is equal to 24. So this is in conjunctive normal form. In order to transform this conjunctive normal form into disjunctive normal form, so that we can easily simplify the query on the consecutive operations of query decomposition, the disjunctive normal form is written as employee number dot employee number is equal to assignment dot employee number, one predicate, and assignment dot project number is equal to P1, and duration is equal to 12, or employee.employee number is equal to assignment.employee number, and assignment.project number is equal to P1, and duration is equal to 24. So this is transformed in disjunctive normal form because the main operator here is or disjunction. But the main operator in between the simple predicates here is conjunction. So it's in conjunctive normal form. For instance, here in between this simple predicate and this simple predicate, we do have conjunction. Again, in between this simple predicate and this mini-term predicate, we have a conjunction operator of relational algebra. So, but when we come to this one, in between each simple predicates, the main operator here is disjunction. For instance, in between this mini-term predicate and this mini-term predicate, we do have a disjunction operator. So we can simply say it's in disjunctive normal form. The second step in query decomposition is query analysis, distributed query analysis, and its main purpose is to eliminate queries which are incorrect. So let's take this simple example where an application selects employee hash from relation employee by a condition employee name greater than 200. So from what we know about relation employee, the column or the attribute named employee hash does not exist. So for this specific reason, we can say this query is incorrect. So the first reason is that the attribute e hash is not declared in the schema. The other reason for us to label this query as incorrect is that the where condition or the selection operation. The selection operation operates on an attribute ename, and as we know, ename is a varchar type attribute, but we are giving it a value whose domain is different, which is a number. So because of these two reasons, this query can be labeled as incorrect query and it will be rejected at the analysis phase of query decomposition. Again, from the semantic perspective, from the meaningfulness perspective of the query, we can further eliminate queries by detecting disconnected query graphs. Disconnected query graphs. Let's take this example, for instance. This application or query projects employee name and responsibility from employee relation, assignment relation, and project relation by a condition, by a join condition, employee.imp number is equal to assignment.e number, and other predicates like simple predicates like project name is equal to cad-cam, and duration greater than 36, and title is equal to programmer. If we transform this query into query graph, as you can see in the right side, we will see a project disconnected, a relation project disconnected from other queries. We can say two relations are connected with each other if and only if there is a common attribute that could be used to join two of these relations. But in case of assignment and project, in case of employee and project, we do not have common attributes that could be used to project data from both assignment and project, or employee and project. For that purpose, we can simply label this query as a semantically incorrect query, and it will be further eliminated from the set of queries or applications. The second step in distributed query processing is data localization. So when we say data localization, it accepts, as a component, it accepts calculus query and transforms it into algebraic query that has enough awareness of the fragmentation and distribution details. So here you determine which fragments are involved, and you try to localize your query pertinent to those fragments which are involved. So basically, this operation is all about substituting each global query by its materialization program. For instance, let's say we have a query that accesses relation employee, and from the localization program schema, from the fragment schema, we know relation imp is further fragmented into employee 1, employee 2, and imp 3, and distributed over the network. So this localization program, or data localization component of distributed query processing, always replaces relation employee by the union of all of the fragments of this relation. So this is called materialization process. So this is how the data localization component transforms one query, one global query, into local query, okay, by substituting each global relation R by its set of fragments. Let's take one example here. We have a relation employee, which is further fragmented horizontally as follows. And also, let's say we have a relation assignment, which is fragmented into two sub-relations based on this primary horizontal fragmentation criteria. Then in the step of data localization, any query accessing employee will access the union of employee 1, employee 2, and employee 3. And any query accessing assignment will be set to access, or will be managed to access, the union of assignment 1 and assignment 2. You can further reduce size of fragments during the localization phase of distributed query processing. For instance, in order to reduce primary horizontal fragments in a distributed data localization phase, we can apply reduction with selection operation. So reduction with selection operation had this one rule, which says for relation R and a set of fragments of relation R, which are FR, where Rj is a primary horizontal fragment of Pj on relation R, then a selection operation Pi on subrelation Rj yields empty set if for all tuple X in relation R, any of these Pi or Pj predicates holds false for the tuple, which the tuple is part of the relation R. So if a simple predicate Pi holds force for any of the tuples of R, or if the tuple predicate Pj, if a predicate Pj holds force for any of the tuples of relation R, then we can simply say the selection operation Pi on a subrelation Rj yields empty set. So for that purpose, we can reduce this selection operation from our set of simple predicates. Let's clarify this rule by example. Let's take a query that selects all columns or attributes from a relation employee by a condition employee number is equal to E5. So as a benchmark, let's say employee relation is further fragmented into three as employee 1, employee 2, and emp3. Primary horizontal fragmentation criteria for each of these is set to be employee number less than or equal to E3 for employee 1, uh, E3 less than or equal to employee number less than or equal to E6 for employee 2 fragment, and E number greater than or equal to E6 for primary horizontal fragment imp3. So by applying the very first principle of data decomposition and localization, we come up with this type of graph. This graph shows the way the employee table or relation is fragmented and distributed over the network. So any tuple accessing employee will be accessing the union of employee 1, employee 2, and emp3. And over the union of this list of fragments, selection operation E number is equal to E5 will be performed. When we apply the rule 1, which checks whether the projection criteria holds for a tuple of each of these relations, for instance, when we see a tuple of employee 1, if we apply project employee number is equal to E5 on relation or subrelation employee 1, we know the fragment or subrelation employee 1 is constructed by using a selection criteria employee number greater than or equal to E3. So from this, by using rule 1 that eliminates fragments that cannot be retrieved by the given selection criteria, we say employee 1 cannot be part of this set of fragments, because if you apply select employee number is equal to E5 on employee 1, you will get empty set according to rule 1. But when you come to employee 2, if we go back to employee 2 declaration, employee 2 is constructed from primary horizontal fragment that takes a condition employee 3 less than employee number less than or equal to E6. So according to our current criteria or selection operation, our selection operation is employee number is equal to E5. So from this declaration, we can assert that the selection criteria here may get some set of tuples from employee 2. So we say employee 2 should be categorized in the set of fragments that could get or that could yield results for the predicate employee number is equal to E5. So we preserve employee 2 subrelation. When we go to employee 3 subrelation, to recall from what employee 3 is constructed, employee 3 is constructed from tuples whose employee number is greater than or equal to E6. In our condition, this subrelation cannot satisfy, or a tuple of any tuple of this relation cannot satisfy the criteria employee number is equal to E5, because all of the tuples in employee 3 are greater than or equal to E6. So for that purpose, we eliminate employee 3 again. So at the end of this rule 1 operation, rule 1 based operation or reduction operation on the primary horizontal fragments, we get a single fragment. So this is what we call reducing primary horizontal fragments. So here, by eliminating fragments that does not have any say on the current operation, we tend to improve the performance of our query. The other technique to reduce unwanted fragments from a distributed query process is reduction with join. But in order to perform reduction with joins, two fragments or subrelations should have the same join attribute and criteria. So the technique that we apply to reduce primary horizontal fragments using join is by distributing join over union. For instance, if we have two relations R1 and R2, which are fragments or subrelations of relation R, Then distributing, then the join between this union of the two relations and another relation S can be further represented as the join between the first fragment and the relation S, union the join between the second fragment and a relation S. So this, we call it distribution of join over union. To formalize this technique, let's say we have a subrelation Ri, which is acquired by applying a selection operation on relation R, a selection operation Pi over relation R. And let's also say we have a subrelation Rj, which is acquired by applying a selection predicate Pj over a relation R. So at this moment, we have two fragments, Ri and Rj. Ri belongs to the primary horizontal fragmentation criteria Pi, and Rj belongs to the primary horizontal fragmentation criteria Pj. Eliminating unwanted fragments by using distribution of join over union can be performed by using this rule. The join between two subrelations Ri and Rj yields empty set if for all tuples x in Ri and for all tuples y in Rj, if Pi does not hold for x or if Pj does not hold for y. So if any of these predicates does not hold for their corresponding fragments tuple, then we say the join between Ri, these two subrelations, yields empty set. So let's take an example here. Let's say the employee is further fragmented into three subrelations according to the primary horizontal fragmentation criteria that we saw a couple of minutes ago. And let's also say that assignment relation, another relation which has referential integrity constraint with employee relation, is further fragmented into two subrelations as assignment 1 and assignment 2 based on the conditions that we see here. Then the representation of this query, select all from employee natural join assignment, looks like this one by materialization operation. So here we have a query that accesses employee and assignment. So when we materialize this query, we have to substitute relation employee with the union of employee 1, employee 2, and employee 3, and relation assignment by the union of assignment 1 and assignment 2. So the first operation here will be to distribute join over union. Here we have unions and unions in both of this set of fragments. So in order to apply join over these unions, we can simply perform a mesh operation in between fragments of each of these set of fragments. So for instance, the join between employee 1 and assignment 1, union join between employee 1 and assignment 2, union join between employee 2 and assignment 1, union join between employee 2 and assignment 2, and finally join between employee 3 and assignment 1, union join between employee 3 and assignment 2. From what we know about the criteria for primary horizontal fragmentation on both of these relationships, for instance, relations or joins between employee 1 and assignment 1 yields some kind of result because the primary horizontal fragmentation selection criteria they both use is the same, which is employee number less than or equal to employee 3. Okay, but when we see the join between employee 1 and say assignment 2, we know after applying the rule here, we know that the tuples in employee 2 does not align or correspond to the tuples in assignment 1 because the primary horizontal fragmentation criteria that we use for both of these relations is different. So in this case, we simply eliminate the join between the two subrelations or employee 2 and assignment 1. Okay. So by eliminating all unwanted or non-participating set of fragments after distributing join over union, we come up with such kind of query graph. So in this query graph, join is distributed over union and unwanted set of fragments are eliminated from this set of relations. The data localization phase of query processing, distributed query processing, can also reduce a set of vertical fragments. So in this case, the operation simply executes or tries to find useless intermediate relations. When we say useless, it doesn't mean relations whose perturbation yields empty set, but we are saying fragments that does not involve in the current application. So let's say relation R, let's take relation R, which is defined over attributes A, where A is comprised of A1 up to AN. And let's say it's vertically fragmented as Ri by using a projection operator over the attribute A prime on a relation R, where A prime is a subset of the main set of attributes A. Then the projection on relation Ri by using the attributes D and K is useless if the set of projection attributes D is not in A prime. That means if the set of projection attributes are not part of the set of projection attributes used in producing the original subrelation Ri, then we decide or we conclude that the new projection is not going to give us any fragment or any vertical fragment. So for that purpose, it will be eliminated from the set of queries. Let's take this example, for instance. Let's say employee 1 is a vertical fragmentation of employee table by attributes employee number and employee name. And also, let's say employee 2 is a vertical fragmentation of relation employee over attributes employee number and title. And now let's take this user query, which projects employee name from employee. So assume we have two employee subrelations, employee 1 and employee 2, that are constructed or derived from the main relation employee. So we can, any operation, applied on this vertical, or any operation applied on employee relation, which is further vertically fragmented as employee 1 and employee 2, accesses the equijoin of its subrelations. So for that purpose, select ename from employee accesses the equijoin of employee 1 and employee 2 by using the join attribute enumber. And after acquiring the result of this join operation, projection is executed. But from what we know in our example, employee 1, for instance, has only two attributes, which is employee number and employee name. And employee 2 has only two attributes, employee number and title. So you cannot find the projection criteria of the application in the second fragment, which is inside employee 2. So for that purpose, the rule here, the rule that we discussed up there, gives the impression that employee 2 might not be feasible to be participated in this query. So we can simply eliminate employee 2 and come up with a reduced set of vertical fragments, which is specific to the query we have at hand. So for that purpose, we have finally select employee name from employee 1 rather than select employee name from employee 1 equijoin employee 2. So this is what we call reduction for vertical fragmentation. We can also apply reduction for derived horizontal fragmentation. The rule is the same as what we discussed before. First, distribute joins over unions, then apply the join reduction for horizontal fragmentation. Okay, so far we have been discussing about the two major components of the query processing or distributed query processing, which are query decomposition and localization. We have seen how to decompose queries by using different operations like normalization, analysis, simplification, and restructuring. And also we have seen different ways of localizing queries by using fragment schema. In the next video, I'll be talking about the remaining topics of distributed query processing, which are distributed query optimization and adaptive query processing, which is pertinent to distributed query plan and distributed query execution.